Okay, so welcome to this video session. So with the given video a while ago on the Poisson's ratio, so let us have a recap on what are the principles and formulas involving those. So we have here Poisson's ratio. So the purpose of Poisson's ratio, as we have viewed on the video, is it tells us how much the material deforms under its lateral direction. So with this, it further presents how different materials deform under loading. Okay, so when we talk of Poisson's ratio, we should note some directions here and distinguish whether it is longitudinal or lateral, longitudinal and lateral dimension. Say we have here a simple figure on the bar. So actually, there will be three-dimensional directions here. Say we have, if this direction along this line, along this line, and along the vertical line. So there will be three axes actually. We have, say I'm gonna label this as X, and this is the Y, and this is Z direction. Okay, so there will be no fixed direction for lateral, longitudinal direction. Depends on the applied load, where your axial load is applied. Is it on X? Is it on Z? Is it on Y? So the Poisson's ratio defines the contraction of the material when we apply a lateral or a longitudinal force along this axis. So perhaps we can have here a scenario. See, if I'm going to apply a longitudinal tension along X, therefore the longitudinal axis, okay, is on X. Okay, so if the loading, wherever is the loading, whatever the axis of the loading, therefore that is the longitudinal axis. Okay, so take note of that. So let us have a scenario. If this will be applied, it is a tension. Of course, it will tend to lengthen this x-axis. Okay. So while this tensile force is stretching this material or lengthening the material along the x direction. By the way, this is the x direction. Okay. This is the x dimension also. So whatever the elongation is, that will be the deformation on x. And if we have a deformation from the original length, there will be a strain on it, right? Because a strain is just the ratio of the deformation to that of the original length. Say if we have here p, no? So habang pinapahaba niya yan, of course, there will be a contraction on the other axis, okay, or the lateral axis. So x here is the longitudinal axis, and y or z will be the lateral axis. So there will be two effects here. This is a condition wherein the force is tension or stretching the material. Kapag compression naman yan, of course, it will shorten the material along the longitudinal axis and it will stretch the lateral axis. So as a behavior, if we need to put that in matrix, we have here longitudinal and the lateral direction. Okay. So if you're forced if your force is in tension along the longitudinal axis, what will be the effect on the, if we have a tension, what will be the effect on the longitudinal axis? Of course, it will lengthen. So there will be a positive length here. Okay? Positive length. So if we have a tension, the effect on the lateral direction would be negative length. As we have said, while we are stretching that one, we are shortening the lateral direction. Okay? However, if we have a compression type of force, of course, we are shortening the length along the longitudinal direction, and for the lateral direction, it will lengthen. Okay? So that is why that is a positive length. So we'll just have to use our common sense in determining what will be the effect of the Poisson's ratio. Now, the Poisson's ratio is expressed by the strain along the longitudinal direction all over the strain along the lateral direction. So let us emphasize that this equation is paired with the negative sign because one of which will be negative. So just the same, we'll come up with a positive Poisson's ratio. Okay? So what is strain? Again, to review. If this will be stretched, okay, so if this material will stretch, it has a corresponding delta here, say this is delta x, and this axis or the dimension of this axis will tend to shorten. So the amount of shortening, so of course, so this dimension is shortening. So ito, paghahatian lang both sides. Same true with this one. Delta x should be symmetrically distributed along the length, ano? Dapat delta x over 2 yan, delta x over 2 din yun. But for presentation, I'll just have that to be delta x. Okay? So for the x or for the z direction, of course, this is the corresponding delta z. Of course, that will be shared but at both sides. And then for the x direction, it will also be shortened along the x direction. And that will be labeled as delta y all over 2, both sides. Okay, so as we can see now, all of the axes will have a corresponding deformation along its original length. So therefore, there will be a strain on it, because recalling that the formula for strain is deformation all over the original length. So there will be strain on different axes, say x, y, or z. X, y, or z. So strain or epsilon here, epsilon could be x. So there is a corresponding deformation along x and a corresponding lx. Okay, same true with y. Strain at y, deformation at y, and ly, same true with c. So what is important in using the Poisson's ratio formula is that dapat alam mo kung ano yung longitudinal at lateral, because hindi naman lahat ng oras nasa x yung ating axial load. So kung nasan yung axial load, yun yung longitudinal axis ng ating material. Say for example, in-apply ko yung compressive force sa Z, then our longitudinal axis is a compressive force at Z. Okay? So the Z axis is the longitudinal axis, and the lateral axis yung Y tsaka X. So, and so on and so forth. So it is very important to note that wherever the location of the applied axial load is, that will be designated as the longitudinal direction. So that we can apply this Poisson's ratio. Okay? So here we have also 3 types of deformation. We have uni-axial deformation, and we have biaxial deformation, as well as triaxial deformation. Okay. So by the terms itself, alam naman natin yung uni, bi, tsaka tri. Uniaxial, it is having a force on a single axis only. Although we have a force on a single axis only, or the parallel axis, may effect pa rin yan on the lateral direction. Okay? May effect pa rin yan on the lateral direction. So in this condition, Hooke's law is applied. Okay, our Hooke's law is applied. What is Hooke's law again? So let us recall that Hooke's law is modulus of elasticity, wherein the stress is directly proportional to the strain, or simply E is equal to stress over strain. So if we have a unique axial, we can apply this one. But in this one, we will apply the generalized Hooke's law for this one. So the same principle, this also applied, however, superposition is applied. Principle of superposition is applied. Okay, so we will now have the derived formula for this biaxial and triaxial. Yung uniaxial, just refer to the formula that mu, or Poisson's ratio, is the ratio of the longitudinal strain to the lateral direction strain. Okay, so for biaxial, we will also talk on strain. Okay, so for biaxial deformation, okay, let us identify one longitudinal and one lateral direction. So let us just stick yung example dito na yung ating force lies within the x-axis. So therefore, the x-axis here is the lateral axis. So biaxial deformation simply is this equation. The strain on the lateral axis, strain on the longitudinal axis, is equal to the strain along that longitudinal axis. We'll just have to subtract the strain on the other lateral axis. Where's that lateral axis? The axis where another loading is applied. Say if we have a lateral axis, say y, we will just multiply it by the strain of y, and the strain of y is given by this one. Okay, sigma over E. So saan galing to? To galing yan sa Hooke's law. This came from the Hooke's law, wherein we can interchange that one by cross multiplication. Strain is just equal to sigma all over E. That is why sigma all over E here is the strain along x deducted by the Poisson's ratio times the strain along the y-axis. Okay, so that is for the biaxial deformation. So it includes longitudinal less the lateral strain multiplied by the Poisson's ratio. So moving on to the triaxial deformation. Again, we will just select a longitudinal direction here, say strain at x is just equal to the strain at x. Okay, this is the strain at x less Poisson's ratio, strain at Y, less Poisson's ratio, strain at Z. So if we are going to simplify that one, then we'll be having here, we can bring out the modulus of elasticity. So naiwan yung sigma x minus, we can actually bring out negative mu there. Okay, so ang naiwan is the sum of the stresses. So this is the formula now for the triaxial deformation. So always remember, kapag longitudinal direction, nandun yung ating axial load, and then yun yung ilalagay dito sa outer, or the outer strain. Okay, so that's the principle or the concept. So moving on, we also have what we call the volumetric strain. Volumetric strain, so it is the measure of change in volume of an object under loading. Measure of the change in volume of an object under loading, of an object under loading. So it is expressed, of course, simply, this is just a proportion. So ilan ba yung delta or change in volume all over the volume? So this is the volumetric strain. So it is usually denoted by EV. And if you wanted to have a volumetric strain for a 3D or triaxial deformation, you just have to add all of the strain along X, Y, and Z. Okay. So a variable to relate with the resistance to a certain volumetric strain is what we call K, or the bulk modulus of elasticity. Okay, so for the bulk modulus of elasticity, or what we call modulus of volume expansion, by the word itself, modulus of volume expansion, it is the amount of resistance of the material to change in volume without change in shape. Okay, so when we say change in shape, so kung cube yun, cube pa rin yun, kahit na humaba or it was shortened. So let me write here now the derived formula for K. again, we will refer to modulus of elasticity because Hooke's law here applies. So 3, 1 minus 2 mu. Okay? So it is also equated to this sigma all over the volumetric strain, delta V all over V. So this is the modulus of, or bulk modulus of elasticity. So this is the resistance to change in volume without a certain change in shape. Okay? So another variable we need to explore here is if we have a cutting force. Of course, we all know that the shear is a cutting force, or the stress caused by a cutting plane or cutting force, or a tangential force applied to a certain surface. This shearing stress will tend to slide the material. So if there will be a slide or twisting on the material, there will be an angle here that will be developed, okay, on the element of the material. So this came from the formula of the strain. Remember that the strain is deformation all over the original length. Ito, pinalitan lang natin yung symbol. Instead of strain, it will become the shearing strain. Okay? So shearing strain, just have this symbol. This is equal to the deformation or the shearing deformation all over the original length as well. So this is the original length. Okay? So this involves rotation, of course. So if there's rotation, it will also involve here angles, okay, the angle of tilt. So for synonymous to modulus of elasticity is what we call modulus of rigidity. Okay, so remember that modulus of elasticity is the ratio of the shear stress to ratio of stress to the strain. So this time we'll just replace the modulus of elasticity E to G if we are in shearing deformation. So instead of stress here, will become tau, or the shearing stress, all over the shearing strain. Okay, so that is for modulus of rigidity. So modulus of rigidity G is analogous to modulus of elasticity in axial deformation. So only that the stress in axial deformation is being replaced by the shear stress on the shearing deformation, as well as the uh, shearing strain, or the shear strain under the shearing deformation. Okay, so expanding further the formula here, so we have to substitute here V over A for tau, or the shear force all over area, all over the shear strain, which is expressed as delta S, or the shearing deformation all over L, and then by manipulation we will have an equation equivalent to the deformation under shearing, which is VL all over AG, or V over A here could be replaced into tau times L over G. So parang ano din yan, PL over AE. Okay? So instead na P, we'll use the shearing V. Imbis na E, we'll use the modulus of rigidity for G. Okay, so as simple as that. So I think we should have an examples now. So problem number 1, we have here a 25 millimeter diameter rod is subjected to this force 117.81, where the strain is observed to be 0.0012. So the Poisson's ratio is already given, 0.33. We're going to compute E, or the Young's modulus of elasticity, the bulk modulus of elasticity of the rod, and the shear modulus of elasticity of the rod. So this problem is all about familiarization on the formula, because first and foremost, from the stress, we can already determine that right away. Okay, because from stress, we can compute for the strain. Anyway, meron naman ng strain. Kung alam natin yung strain at alam natin ng stress, stress all over strain is modulus of elasticity. So a simple quotient will give us 200,000 megapascal for our modulus of elasticity. So for bulk modulus of elasticity, we have introduced the formula. All we need is to substitute the values here as together with the Poisson's ratio of 0.33. So we have 196,078.43 megapascal for our modulus of volume expansion, or what we call bulk modulus of elasticity. And then for the shear modulus, if we have E and if we have Poisson's ratio, it's just given by this equation. G is equal to E all over 2, 1 plus mu, and we will arrive at 75,187.97 megapascals. Okay, so moving on to the second problem, we have here the solid cylinder. This is 6 meter long, is subjected to 30 kilonewton. So 30 kilonewton here is parallel to 6 meters. So therefore, along that axis, along the 6 meter axis, is our longitudinal axis. As we can see here in the diagram, there will be a stretch along the longitudinal axis and a shortening along the lateral axis, which is y. So we are going to determine the reduction in its diameter. So here, the reduction, is on diameter. It is equally shared along the edges along the y-axis, so that is why it is labeled as delta y all over 2, as well as the x is distributed on both sides, that is delta x all over 2. So recalling the formula of the Poisson's ratio, it is the ratio between the longitudinal to the lateral axis. And what is the longitudinal axis here? The longitudinal axis here is along x. So that is why we have here y as the lateral axis. Yung nasa baba, yun yung longitudinal axis. And that is denoted by a negative sign. And then by cross multiplication here, okay, we will arrive at this strain at y is equal to strain at x times Poisson's ratio. So we still do not know what is the value of strain along x, but we can actually get that right away. So recall the formula of the deformation. On the axial deformation, we have PL all over AE. Okay, so substitute all the values. So along x, we have a cross-sectional area of a 75 millimeter diameter bar. So just substitute that one, and then we arrive at 0.204 millimeter delta X. So if we know delta X, of course, kapag may deformation, just divide that by the original length, and that will be the strain along X-axis. So we get again the value of the strain along the X-axis, substitute, okay. So here, let us note that we must have to multiply the strain along Y by negative Y, because as we can see in the figure, the Y-axis has actually shortened, okay. So if that is shortened now, still, babalik tayo sa positive, and then substitute the value of the strain at X, and then by the Poisson's ratio, we multiply that, and we come up with the strain along Y. So relating to strain to deformation along the diameter, so ito, i-apply lang natin yung formula ng strain. This time, it is along Y because we have already obtained the Y direction, okay? And the original length is actually the diameter along Y, okay? So ngayon, we'll just substitute that one by cross multiplication. It will be directly multiplied by the 75 as the diameter of the Y-axis, or the length along the Y-axis. So by that, therefore, the deformation is 8.4 times 10 raised to negative 4 millimeters. Okay? So that's it for the second problem. So for the third problem, we have here a steel block. By the way, the second problem, ito uniaxial lang to because there is only one axis that is subjected to an axial load. Okay? So for problem number 3, we have a rectangular steel block that is 75 millimeter long in the X direction, 50 millimeter. So all of the length of the axis are given. So the block is subjected to triaxial loading. So ngayon meron na tayong triaxial. So all of the axis will be having a force. So meron tayong 220 in the X direction, that is elongation or tension. 270 along the Y direction, and that is shortening or compression. And 240 kilonewton in the Z direction, or that is stretching. So given here the Poisson's ratio as well as the modulus of elasticity, determine the force in the X direction that would produce the same deformation in the Y direction as the original loading. Okay. So the unknown here is kung meron tayong block subjected to this triaxial loading, magkakaroon tayo ng, it will produce a strain in Y, X, or Z direction. So all of which will be having a strain on corresponding axis. But the problem focus only on the Y direction. Okay? So Y direction. So magkakaroon siya ng strain along Y direction as well as deformation. Ngayon, ang tanong, kapag tinanggal natin lahat ng loading, okay, using the same cube here, anong dapat na force sa X nang sa ganun parehas yung effect ng tatlong loading na to or this setup? Okay? So again, ito lahat yan will have a strain along Y. It will produce a strain along Y and deformation along Y. because of the triaxial loading. So, pag nakuha na natin yun, we will remove all of the loading and then apply a force along x direction so that it will have the same effect or the same strain along y and the same deformation along y. So, una, kailangan natin malaman kung gaano ba humaba yung y. Asan ba yung y? Ito y. Humaba ba or umikli? So, it should be shortened, ano? Because the force along y is in, this is in compression. So, that is in compression. The strain in y should be negative in nature. So, anyway, this is the formula. By triaxial deformation, we have strain at y is equal to 1 all over E. And then, all we need here are the stresses. Okay, sa formula, kailangan natin ng stress, ano? So, all stresses along the axis will be computed here, starting at x. So, nasan yung x dito? So, along x, we have 220, and that is tensile. Tensile loading times 1,000 to make it in Newton. So, let us investigate the dimension. Okay. So, yung dimension ng, or the area along x-axis. So, if this is x-axis, of course, the perpendicular area on that. So, ito yon. So, kung titignan natin yan, that is 50 by 100. So, that is 50 by 100. Okay? So, we come up with the corresponding sigma along x. And along y, we have a compressive stress. Because this is compression, 270. And then, the area is this one. 75 by 100 dimension. Okay? This is 75. And that is 100. Okay. So, we have 36 megapascals for that. And then next z, ito yung nasa ibabaw, 50 by 75. So, just copy the 240 there times 1,000 times the area. So, we have 64. So, after getting those one, we'll just have to substitute in this equation. But remember to indicate the negative sign for a compressive stress. So, kapag tensile stress, that is indicated as positive in this formula. So, doing that, magkakaroon na tayo ng strain equivalent to negative 3.42 times 10 raised to negative 4 millimeter per millimeter. So, as we can see, the result here is in negative, only indicates na yung strain at y is negative, which means tensile force prevails at perpendicular axis x. Okay. So, now that our strain is known for the y-axis, so ang tanong, ano daw yung katumbas na force that will be applied along x when we have a uniaxial condition or stress between x and y? So, we will go back to the formula involving the uniaxial stress, which is the ratio of the lateral or the lateral axis to the longitudinal axis. So, yung longitudinal axis natin is nasa x, and then the lateral axis is along the y. So, we're just gonna use this one and then come up with ito, strain at x. So, pagkatapos ng strain at x, kung may strain ka, meron kang deformation. Kung meron kang deformation, then we will have a stress, and eventually, we will have a P. Okay? So, yun yung link. So, yan. By direct substitution, sigma or strain at y is negative 3.42, we will come up with the strain at x 1.14 times 10 raised to negative 3. Okay. And then applying the Hooke's law, we have modulus of elasticity is stress over strain. Along x direction, we have 1.14 times 10 raised to negative 3 times, yun, by cross multiplication kasi, itong strain, diretso na multiply sa strain along x. So by that, we have the stress along x is equal to 228 megapascals. Okay? 228 megapascal. So, kung alam mo ng stress din, malalaman mo na rin yung force. Okay? So therefore, by cross multiplication, we have here 1,114,000 Newton, a tensile force to be applied along x. Okay? Tensile force to be applied along x, so that we can satisfy the same effect by these three forces along x, y, and z direction, or the triaxial loading. Okay? So that's it for number 3. So for number 4, it is just a follow-up question. For under number 3, what load would be added along the x direction for the block described in problem number 3 in order to produce no deformation in the z direction? So when we say no deformation, therefore the strain is 0, because yung strain, di ba, it involves the deformation divided by a length. So if the deformation is 0 divided by a certain length, still that is equivalent to 0. So we determine what type of strain along the z direction, and then we indicate that if z is positive, then triaxial loading had caused it to elongate, and if z is negative, then the triaxial loading had caused it to shorten. Again, we will refer to the original loading, only that we will set strain along y, along z to be equal to 0. Ano? So from this, nakuha na natin kanina yung x, y, and z stresses, and we found out that we have x 44 tension, y 36, and z 64 tension. Then we will apply the strain formula for triaxial loading, calculating for the z. So substitute the values here, indicating also na negative pa rin yun, ano? Sa y is negative pa rin yun, nakalagay dito. And then we will have a positive outcome. So what do we mean by positive outcome? Results yielded to positive, which implies stretching of the fiber along the z-axis. So ibig sabihin, nag-stretch yung z-axis. Kanina negative. Okay? Kapag negative yan, it will compress, or y-axis is just compressed or shortened. Okay? So going back to this, we have strain at z is 3.08 times 10 raised to negative 4 millimeter per millimeter. So results yielded to positive, which implies stretching of the fiber along the z-axis. Okay, so illustrating that now, to be able to set deformation at z to 0, an additional, kasi nga, di ba, sabi niya, yung z natin is 3.08, nag-stretch siya. E paano mo ibabalik yon? Kung baga, pag humaba yan, ibabalik mo siya sa dati, in order to come up with no strain at z-axis. So, saan mo i-apply yung yung force para bumalik yan. Okay? So, an additional delta px along x should be added. So, kanina, so, yung tanong sa x-axis, ano? What load sa x direction tayo ngayon, sa x direction? What load would be needed along the x direction for the block described in problem number 3 in order to produce no deformation in the z direction? So, anong gagawin natin sa x? Stretch ba natin yung x or i-compress? So, that will be answered by this result. Yung ating z humaba. Kapag humaba, ang kailangan natin gawin ang ibig sabihin ng humaba sa z direction, z is lateral, ano? Kabaliktaran dapat ang gagawin sa longitudinal axis x. Okay, kapag humaba yan, tension, di ba? So, yung lateral natin dapat ngayon is compression. Pero, i-reverse natin. So, kailangan, we will be having a stretch also along x-axis. Okay? Did you get that one? No? So, yung z humaba because this is positive strain. So, para bumalik yan, stretch natin yan. Okay, para bumalik, stretch natin. Babalik yan sa dati. So, when we stretch this one, of course, the lateral axis will be compressed. Okay, ano ba yung reverse ng tensile? Compression. So, we're going to reverse that by having a tensile force here. Para yung humaba kanina, i-compress natin ngayon para bumalik sa dati. Okay, so applying the formula. So, ito lang naman, sinolve natin in order to determine kung humaba or umikli yung z-axis natin. Nang sa ganon, malaman natin kung kailangan ba nating stretch or i-compress yung longitudinal axis so that this must be reversed in order to have a strain is equal to 0. No? So, balik mo yung formula ngayon. Okay? And then set z is equal to 0. Using the same stresses a while ago, then we can compute for sigma x, okay, or the stress at x found to be 249.33 megapascal. Yun, makukuha na natin yung ating force along x, 1 million. Actually, this is 1,246,666. Sorry, 1,246,666.67. So, this is in tension. Ito yung kabuuan, okay? Ang sinabi kasi dito yung kailangan mong idagdag sa x para bumalik yung z-axis. So, kaya dito, we are going to deduct the original loading which is 220,000. So, yung additional dapat 1,026,666.67 Newton in order to come up with strain along z-axis. No strain along the z-axis. Dapat 0 yan. Okay, so again, binalik natin yung stretch dito caused by the triaxial loading by adding here an additional tensile load so that this will be stretched along the longitudinal direction and then compress along the lateral direction. Okay, so just remember, kung ano man loading sa longitudinal, kabaliktaran ng effect sa lateral axis. Okay? kung yung longitudinal mo is a stretch, yung lateral mo is a shortening. Kung yung longitudinal mo naman is shortening, yung lateral mo is lengthening. Okay, so lagi yang magkabaliktad. Okay, so for the fifth problem, we have here the uniform shear stress of the beam. Neglecting the beam's weight, we are going to determine this. If we have here a short beam here with this dimension, and then this is an overhang with a length of 800 millimeter, and a pointed load is applied at the edge of this cantilever beam. Shear stress, neglecting the self-weight, the uniform shear strain of the beam if the shear modulus is 24,200 and the deformation at free end. So in this case, we are referring to a shear stress. Okay? So talking of shear stress, if we apply 100 here, magkakaroon tayo dyan ng 100 na reaction. So in short, it is assumed that the shear along whatever section here, no, 100 lahat ng ating shear. So the shear is constant all over the cross-sectional area of the beam. So given that, the uniform shear stress could be determined. Okay. So as for the uniform shear, we'll just have to apply this formula, V over A. So your shear force is 100, because as we have said, 100 is constant all throughout the beam. So the area is 150 by 400. So we have a shear stress of 1.67 megapascal. So knowing our shear stress, just substitute that in the formula of modulus of rigidity. We have 24,200 is equal to, then we have the shear strain here, 6.9 times 10 raised to negative 5. So the answer here is, again, this is an angle, okay? It involves rotation. So therefore, this is a radians unit. Then finally, the shear deformation is, by substitution, we have to cross multiply that one. Then we'll be having here a delta equivalent to 0.055 millimeter. Okay, so it is just merely substituting or relating to the formula para din niyang similar sa sa axial deformation. Okay, it is similar to axial deformation na meron siyang P over A, stress over strain, meron siyang delta all over the original length. Yan, ganun din dito sa shear stress. Okay, next. So on number 6, we have the bulk modulus of a certain steel cubical section, 170,000 megapascals, and the Poisson ratio is given. Number 1, the Young's modulus of elasticity is required. Okay, so we'll just have to do it by substitution, and then we come up with modulus of elasticity, or the Young's modulus of elasticity, and then the modulus of rigidity. So relating it to our elasticity as well as the Poisson's ratio, we just substitute the values. We have value for G. Okay, so for volumetric strain, there is a relationship between the volumetric strain also with regards to the stress. Okay, so with that, if we have a volumetric strain, so the compressive stress on the faces of the cube if the volume was reduced by 0.2%. So 0.2% is actually the volumetric strain. Okay? Because this is a percentage. So ilan ba yung delta with respect to the original volume? Ilan yung nabawas na volume comparing to the original volume? That is a percentage, or that is 0.2% or equivalent to 0.002. Just substitute in this formula K, or the bulk modulus is equal to stress all over this one. So we will have the 340 megapascal stress for this, basing from the bulk modulus and the volumetric strain. Okay, so letter D question. The bulk modulus, compute the bulk modulus if 180 megapascal stress acting on each side had caused 0.25% volumetric strain. So again, we'll just have to replace the given here and then come up with the stress of 425 megapascals. Okay, so that's it for this session. So I hope you will practice more problems on the given material to you. So thank you, and have more practice.